Alright, I am back. This time we're doing Cleanhouse now. While I was making coffee to make this, I came up with an ideal to use heat map, maybe, to do this decoding part. So, if that ends up working, hold on, I gotta change the song. If that ends up working, then cool, but I mean, at the moment, I still have to do a review for how it is right now. So, the Cleanhouse seems to be, I think it's simpler. Originally it wasn't. I've made it more simple. I think I might have a way to make it even more simple, where it matters even less about tons of stuff. So right now there's a lot of information that has to be assumed. At the moment, this thing right here, we have to assume this instructable. I have not made it set up to where we can actually detach this, but I need to, because the ideal I have to do the decoding, it would be I would definitely have to have it. At least copy and paste that set of information over here. Well, I believe it's inside the full house instruction set, not the main JavaScript instruction set. And that one is only invoked at a certain time. So this one, we would have to pretty much just, after we get to a certain point when we start doing the detangling, or the decoding after the detangling. No, I guess it is detangling. This would help us to restore a lot of that out. So we're going to get through it. So here we go. We got grabber. We know we're using grabber. Snagger. Definitely using snagger. Marble. Definitely using marble. In this case, it was more like rolling a marble down, but marble and tracker are damn near the same ideal. I don't remember what PSG actually stands for anymore. But there's a W, then there's a 1 with a W. I don't think these are being used. Let me see. Oh no, it definitely is. Previous subgraph. That's what it means. It means previous subgraph. And now previous subgraph W. Yep. It's just basically a second version of previous subgraph. So you can do manipulations and stuff like that. And this would be, this would just be an additional set. Yep, and looks like there is a couple of other ones coming up. XSG1 and ISG1 are going to be coming up as well. Okay. These are all the detectors. The programming slides. And then the actual rows themselves. So what we do is we take snagger and we just take whatever the input is. So we're basically this is doesn't cover but I mean, it doesn't cover like if someone's sitting there typing it in one at a time. But it does actually have a thing where you could do that. It would be really confused all the way up into the time that you actually get done, and it could actually cause a bunch of problems. So I need to put in a thing that is basically looking for that. So there needs to be some kind of loop that looks, and there used to be a loop that would specifically look for errors, and because those have to be dealt with ahead of time. So I would be just be opening up that loop, and instead of looking for errors, we would need to look to see if they're inputting. Alright, and then simply, after we get all the snagger, it ends up being, like, they end up just being separated by a bunch of whatever. So we remove that separation unit to make it like one big long thing. So now that it's one big long thing, no, it's not. Okay, so snagger is the whole thing. Snagger len is the length of snagger. To find out the length of snagger, it just takes snagger and splits it up by these, right? And it finds out what is the length after doing that. So it can then go, every time it sees one of those, it'll count it as a 1. So, so we'll get a length total from that. DPSG1, so this again is pre-subgraph, but it's D1, and then D1C1 the main, D2C1, D3C1, D4C1. So we have layers of C as well as the actual graphs themselves. And as you can see, there's, I believe, up to 4. So there's 1 equal C for 1 equal layer. So, and they all have to run on there. And in between each one, you'll see, like, after the C1 set, we will have, before the C1 set, we have the D1 or the D for the PSG1. And then here's the D for the PSG2, which then goes through all of the Ds here. Again, and we have the 3 within all the C3s, 4, and then all the C4s. So then we have the 3 main rows, the next set of the 3 main rows. So basically you have a standard, which is an A, which is what you had to get it, B, which means it's in processing, and then C, which means it's done. It's ready to go. Okay? So which is why we come up with C usage over here. And then we have the same thing for null as well. All 3 steps. So then we have shape, which I don't know if I'm using shape. No. I'm not using shape. I don't think I'm using temp shape. Because I don't need to. And these are all the shape thingies that I'm not using either. So I'm not using any of that. I don't know. Oh, I thought I was still using this. I might not still be using this one. Nope, I am still using it. Okay. Obviously, it's either for error correction. This actually tells us the position of a noticed error or potential error, and this is the code that error gave. And codes can be or numbers. And then every time an error code is given, there also should be a spot where we are getting the error data. So yeah, do it like that. Just do empty state. Alright, so here we can see it just basically says, hey look, if we end up with nothing in the text field, just clear everything out. And kind of like last time, I have to ask, let me put it down here. Okay. So now we're going to start prepping data, which is, I think this is where one of the errors is definitely happening. So I know that this works, and all this does is it looks to see if we have a graph, and like is there a like what kind of graph? Because if it's a subgraph or regular graph, let me show you what I'm talking about. Cause most recent save, yeah. So we have a graph. So orange is a color. Orange is a color. I messed that all up. Yep. Let's try it again. Orange is a color. And orange is a color. So here's the main graph, and you'll see it looks a very specific way. Here's the subgraph. It has a new front. Instead of giving us a block header like this, see, this block header is right here. We actually lose the block header. And if we was to take this information right here, copy, so this right here, this information, 418E35, and then so if we take this is what should be inside this one. (417E17). And if we open it back up, it does say 417E17, and if we're inside of here, it actually says 417E17, and if we go back inside here, 418E35, just as it said before. So now we have a way to determine if something is a starting of data and if something is in the middle of the data, or potentially end. And so each one, so even though I don't know what this one is, I can find out what this one is. It's right freaking here, right? And I just have to base 64 hash this, and boom, I have my answer. And then I can just base 64 hash this, and I can find my previous. So I can always find the one before it. And you'll notice this is actually less characters than this, which is why the very first one we just used the hash, because we don't have to worry about character sets. Everything after that we have to start worrying more about character sets, so we drop it down. Simple. We make it easy. We keep it simple, and that's what I'm thinking that we're going to have to do. I think I'm not keeping it as simple as we could be keeping it, and that is where my problem's occurring. But anyways, so this looks for that just fine. This is the setup for base 64 to find base 64, so it works, okay? And if you look, it says it's actually designed to look for data graphs and not data graphs. For example, orange is a color, right? So we're encoding. I'm just going to do one more. So here's the new one. I'm going to go here. So if I was to like try typing one of these in by hand, just forcefully simulate this. You notice it's not saying it's not a data graph. Now it's saying it's not a data graph. So even this has potential to actually be a data graph. Of course, it isn't, so it's not going to work. But if we was to just go back, we grab that data graph. Now it's a data graph again. So we have potential to be able to set it up in a manner. Oh look, we can actually see that there really is an error, even though it's not showing up. We can see there actually is an error right here. And to be honest, this is because it's not performing the right parity check. I know that. So I know it's only doing one of the 8 possible parity checks. So, and this one should be triggering a different parity check, but it's not. We don't have it in there yet. And I figure there's a reason to put it in. If the rest of the decoding ain't working, why worry about that part of the decoding? Just because it's further down. I kind of do these top down when I do a lot of this stuff. And what I do is I'll just make something work. I'll just get something to work. Alright? And then I'll be like, okay, this is working. Because at one point in time, the decoder was doing its job. And it was actually finding stuff. And it was finding, what it was finding, it was actually finding stuff. So it wasn't finding what I was wanting and stuff like that, but it was doing its job. And then I got the encoder working better. And now the decoder stopped working. And then I went through and worked some stuff out to get the decoder to potentially just work more correctly. Because I had some weird bug that I didn't notice from a long time ago that I had fixed that caused the decoder completely just stop working. And now the only thing that's not working is the mining out is not working, so I can't see if I'm actually finding anything. So at one time it was working, so I get something to work, and then I try to make it either smaller, simpler, easier. So a lot of times when you're doing this stuff, that's just get it to work. Okay, that should be your first goal. Get something to do what you want, and then figure out how to make it faster, easier, simpler, better. Just work those one at a time. Like I normally go, okay, what's simpler, or what's easier, and then I'll go, okay, now is this faster, or can I go faster than this? Sometimes when you make stuff simpler, it makes it slower, and sometimes when you make stuff simpler, it just makes it faster in general. So your goal is to just guess and hope, well, not guess, but hope that you can find something to make it faster, or you hope that it is as fast as you can get it. So, I mean, either one of those, like, in other words, like, if you can't find something to make it faster, or you can't figure out a way to make it faster, but it's working and it's simpler than what it was before, it probably is as fast as it can go. That's really what I'm trying to say. So, okay, anyways, all this is doing is breaking down everything. It's finding each one of these, and it knows, okay, the very first thing we find is this. This is the very second thing we find. I mean, like, the very first thing we find is this. This is the breakdown to determine if we have this, what to do. If we find this, what to do. If it's this, this is what we do. Here's D1, determiner 1, and then determiner 2. And we just know where they are based on here. And then, so P3, as we can see here, I'm still having problems remembering some of this information. So this tells us how large at the end is and how many slots are in the longest row. We don't know which row that is. We use Michelle to determine how long a row item is after the Futurama Theorem. So basically the ideal here is, yeah, we only know the external length of the subgraph, the very first number, and the internal total byte size or recorded weight. Because it could be either one of those is the second number. No, my bad. NXE. So the internal total byte size is the middle one, and then recorded weight is the last one. I guess at one time it was either, but now I guess I do have it set so it does both. Let me just go back and look real fast. XE, yeah, it does do. Yeah. So it's saying that this takes at least 4 loops, with a consideration of potentially 18. Now 18, we know that from this point on, we've been using this number right here as a guaranteed no. We don't hit that, we're doing something wrong, right? This used to be that number, but now this is more like sequence and order. So like, if I go to the next one, what was the 35? No, so they're all 4. Yeah, I don't know. We might have to see what's going on there. There might be something up. I need to mark that. Okay. Well, anyway it goes, it knows what to cut with and why, what to look for after. And I do want to make this more variable, like would like x to be replaced with to be replaced with. Now, originally, we were using x because it's blank times blank, and e is like in multiples of whatever, like 10 times, 10 to the 10th power or whatever, right? But there are variable versions for these, so they need to have variable possibles. Okay. Alright, so here D3, okay, so 5. Here we have a really good note here. So if record the first step variable, then compare after across the array. We don't actually do this last part anymore. Very first step variable. So notice this is row 1. So the very first thing we need is that very first variable. So it says drop row into new array to run through the Futurama Theorem. If it starts with 0, run the standard. If it starts with 1, run the offset. So we actually have two different equations, and you'll see them to handle this. It's a modified Futurama theorem. It's to handle figuring out what to do with what is the next thing. So we can see we just take the very first one. I don't know what it is. Throw it in there. And we're going to be doing same thing each time. Now, a long time ago, I figured out a way to do that in like one simple trick. What the heck is that? Flat map. I don't remember. But there was this thing where I was doing with flat map, and then we just change everything after that, but can't remember. Alright, so do it again, do it again, do it again. Okay, so null yeah, null's the same thing. Yeah, they're all the same. They all do this. There we go. Oh yeah, it does say error found. So yes, I can. If it would look just a little bit lower, error found. This is also where we found the decompression error. Oh yeah, that's been marked out. This is that's gonna get much bigger later in the future. So now we need to turn these strings into arrays. And we're using ground to do that. We're using a grounder. And so we take the length of each. We get the length of each. So we know how many loops we're doing, all that stuff. So if we take an n and we take the and then 0 and then 1 and then 2. Oh, n2 is an exit loop. Okay. So n0 is less than grill. We push, or else we check these, make sure any of these are not. So basically, we want all of them to be ready at the same time. So don't exit variable if another row isn't ready to hit its limit. So it just kind of looks around. Hey, are you guys ready? And I'll say, no, I'm not ready, and it waits. So if he's the last one ready, he'll activate. So that's what enemy in all of these. If you're the last one, activate. Otherwise, just keep on going. We'll, find it. So if grill's less than, this is what they do if they don't. If once they do, they go to this. Okay. And we're gonna do that for all of them. Yep. 1, 2, 3, 4. question in there. If I could do this once, but just change what this variable is and what this variable is based on the loop. So the very first time I do it, it'd be 1 and 1, second time it'd be 2 and 2. And I just have one loop to one. You know, you can just get rid of all this extra. That'd be really nice. My brain's saying, so quirky value, so we go var equals quirky value. Loop number, so number, and variable quick value equals plus loop number. And I need to go that. And go if less than quirky value. Oh yeah. Quirk equals gr plus loop number. See, here's where it gets to a problem. It wouldn't push to the right place. Well, I guess here would be like, right, because quirk value is not a value, is it? No, it's that combination of things. Yeah, so I can't figure it out. That's something I'm gonna have to figure out some other time, maybe. I don't know. But this does look. I do see where we're seeing inner loop. So maybe this is that one spot where I was like, what? Let's go to 4. So once we exit that, N2 is less than 4. So all 4 of them have to actually be ready to exit. They all have to exit simultaneously. So they exit. Okay, cool. That teaches us to go through all of them each time. Alright. We are increasing n in 0 each time. And it does start at 0 and then I don't ever use n in 1. Not that I did. No. Start off at 0. I was saying to myself, this will go through each time, so 0, 1, 2, 3. In my head, I got 1, 2, 3, 4. And I'm like, oh no, when it does this, if this is 1, then. But it does start off at 0. But it should do this. Wait a minute. Are we having problems with the system getting confused when this loop order ends and when this loop order starts? I hope not. Used to not. I think it might be. It used to work right here. This used to work. What happened? Let's see. If we go to the old encoder. Is there really a 0.001 in here? Yeah. There it is, right there. Okay. There's another one. Oh, space. Huh. Yeah. COORANGE space IS space A space COLOR. Ah, this is all the excess. This is because it used to do a random accord to get to a certain length. Ensure you with the length. So this part is still seeming to be working perfect. It takes all of the stuff, takes it apart, so it is not properly. Okay. Alright. I need to at least get through talking about this before I can start making changes. So now we go through the actual Futurama Theorem decoding. Green, red, blue, all the links. Full stop, okay. So we need to follow R1 line to adjust the flat map. Yeah, see, I was intentionally using a flat map. Start the rewrite position. Wait a minute. Oh, this is actually the mining part, so... move that down here then. So blue is the exit. Alright, so if red is less than grill, start the inner loop. Yeah, red is 1. Yeah. I'm gonna try something really weird. Let's just try real fast. My brain just told me we already recorded the very first one. Okay. What are we pushing this data to? To the main rail. I'm pushing stuff to the main rail, right? Okay, so then we pushed everything from the rail to this rail. Definitely something's going on here. Alright, I'm gonna have to stop. I know I'm nowhere near the end of this decoder, but I gotta go take care of something. And I'm gonna have to just, I think I just figured out, I think this right here, and then I think this is the error. I think this is the error for the mining not working. And then after I do some stuff, I'll go back on later tonight and show